Okay, so the next part of it is to, as I said, come back more specifically to the ocean. So start with the rise in ocean heat content. So this is heat content in joules per meter squared for various depths of the ocean, starting in 1960 and going up to about 2018 or so. Though the gray line here is showing ocean heat content down to 300 meters from the surface down to 300 meters. The bluish line is showing down to 700 meters. The green line is showing down to between 700 and 2000 meters, and the yellowish line is all the way from the surface down to 2000 meters. So you can see that the main message is that the upper ocean is acquiring heat for a while, you can see, and the 700 to 2000 meters was fairly flat for some years, but it's increasing more recently. So the heat into the ocean is penetrating deeper and deeper. So if you remember your ocean circulations, the main thing to remember is that it's not like the atmosphere warms, so the heat is diffusing into the ocean everywhere. So remember the upwelling in the eastern Pacific and so on, where we said the upwelling soaks up heat into the ocean, and there are regions where it loses, like the western boundary currents separating into North Pacific Current and the North Atlantic Current and so on. So the balance is happening, and there are sinking regions where the ocean takes up heat. So there are specific ways in which the ocean dynamics takes down heat. So it's not the diffusion process from the surface. So this is what determines how fast the deep ocean acquires heat versus how the shallow water acquires heat. Okay, so the 700 to 2000 meter is clearly showing the slower warming rate, but of course it started with lower than the baseline, and then they have all gone above the baseline. So it depends on what the baseline is used. So you can see here these are negative numbers, and we have jumped out of into the positive here, and you can see when you look at the surface to the bottom, the heat content was quite low compared to the baseline, but now the deep ocean is also warming, so the entire ocean column is warming down to 2000 meters. So you may not get a sense of how big this 2 joules per meter squared is, but if you consider the heat content of the water and how much area the ocean occupies, you can see that the global mean increase of couple of watts per meter squared can be more than the entire electricity production of the world. So, and remembering, as we will see soon, that ocean takes up 93% of the additional heat trapped by the increase in greenhouse gases, this is almost all of the additional energy that is that we are trapping because of the increased greenhouse gases. Okay. Here is another way to look at it, by also including land and ice and atmosphere with its residuals or uncertainties. So we are again showing ocean down to 300 meters, 700 meters, 700 to 2000 meters, and ocean below 2000 meters. So you can see that obviously ocean is taking up more and more heat, and in the top 700 meters and also in the top 300 meters over time, which is a good thing because that heat is then taken away from the atmosphere and is hidden into the ocean and can stay there for centuries or even thousands of years if we are lucky. And the sad news is that even the deep ocean below 2000 meters is now warming, as you can see with the increase in energy. Now we are showing, instead of heat content, energy change in zeta joules. which gives you a better sense of just how much energy is getting trapped in the ocean. So total top of the atmosphere energy balance shows how much energy is being acquired by the system, and there is a large uncertainty there, which is expected, but you can see that that uncertainty band is narrowing over time. So there is a tiny bit that is going into melting glaciers. Atmosphere's heat capacity is very low, so obviously it has warmed by 1.2 degrees centigrade since Industrial Revolution, but you can see that that amount of heat is very tiny compared to the energy that is being trapped by the ocean or even land. So you can see that even the land is acquiring more and more heat over time. What else can we see here? And the uncertainty is there as well in terms of the bands shown here. Okay, but the good news is that we are reducing the uncertainties over time. So maybe I will continue this and show how that translates to sea level rise. So the projections of sea level rise for various scenarios of RCP 2.6, 4.5, 6 and 8.5 are shown here, with the thermal expansion, glacier contribution, Greenland ice sheet, including the dynamics of how the ice albedo feedback and Moulin formation, etc. are working, which I'll show in a minute. Antarctic ice sheet, including the dynamics of the ice movement. Glaciers are compressed snow, and they have a rheology, especially on the slopes they flow. Grounding line changes, equilibrium line where accumulation of glacier and ablation of glacier are equal, changes and so on. Those we refer to as dynamics. Land water storage changes the sea level as well. You are evaporating from the ocean and dumping it onto land. And Greenland ice sheet rapid dynamics, Antarctic ice sheet rapid dynamics, which is the glacier dynamics related to the retreat of the edge of the glaciers and how that is affecting the sea level rise. Because remember, when snow gets locked onto land, you are removing water from the ocean and putting it on land, and glaciers melt, you are releasing it all back. So you can see that the contribution from thermal expansion is large, and other contributions are increasing over time, like the glaciers overall, and there is large uncertainties as well. So you can see the uncertainty bands here are fairly large. So future projections of global mean sea level rise in meters at the end of the 21st century, which is 2081 to 2100, relative to the recent past of 1986 to 2005 under 4 representative concentration pathways shown here. Here is the global mean sea level rise in meters. What is the use of global mean sea level rise? It does show you how much sea level rise is going to be on average, but the dynamics, ocean circulation and so on determine where the sea level rise is going to be large and where it's going to be lower. In some places there may even be sea level dropping below the reference period, for example. So translating global mean sea level to local or regional scale sea level rise is not always easy, especially because as glacier melts, the continent under also moves. When the glacier grows, continent is pushed down. When glacier melts, the continent rises. So the meltwater is distributed globally, called eustatic rise, whereas the continental change causes relative sea level change locally, which is called isostatic change. Anyways, individual contribution to global mean sea level rise over 1993 to 2015 in millimeter per year is related to thermal expansion, which is the largest contributor, as we just saw. glaciers contribute about half of that, and Greenland and Antarctica are contributing some, and there is a residual when you compare to the total sea level rise that is observed. But if you look at a shorter period from 2005 to 2015 instead of 1993 to 2015, you can see that the thermal expansion remains almost the same, but the glacier contribution goes up. So from 0.65 to 0.74, this goes up, and the residual comes down. So glacier contribution has gone up, Greenland contribution goes up by a lot, and Antarctic contribution goes up as well. Okay, and Greenland is now in a really bad shape. This paper just came out this week of February 23, 2022. So this is showing water flowing into a moulin down to the beds of Store Glacier in Greenland. So the top of the glacier begins to melt, and you can see that the albedo here is very different than the albedo here, which means more and more energy gets absorbed, more faster melt happens. That meltwater drills into the glacier, goes to the bottom, which is called moulin, and it acts as a lubricant at the bedrock interface with the glacier and makes the glacier slide down the slope and accelerates the glacier melt processes in many ways, and it builds so-called ice dams in many places. So this paper reports that Greenland now has some of the largest dams of such water that is trapped behind some glaciers. So Antarctica is a more complicated story because the Southern Ocean warming can increase the water vapor and snowfall in some places, and the melting and the melting of the ice shelf or glaciers flowing onto the ocean from the slopes of Antarctica are getting melted by the warm ocean as well. So if you look at the ice melt in terms of thickness change over time, there are many places where it is as high as 3 meters per year, and there are some places where the rates, so it is growing by 3 meters per year in some places and melting by 3 to 7 meters per year in some places. So I will just leave it there, and you can see that the temperature changes also have positive and negative values. So just remember for this introductory class that because of the Southern Ocean channel around Antarctica, and because warm ocean can produce more snowfall in some places, Antarctic sea ice change, Antarctic glacier melt, and so on are complicated, but overall Antarctica is still contributing to global sea level rise, global mean sea level rise. Okay, so let me leave this here, and then we'll come back and continue the story with some more details on ocean's role in energy balance that we have already mentioned several times. Okay, so global mean sea level rise is definitely observed with satellites. It's very easy to figure out that the global mean sea level rise is positive, very high in some places, especially low-lying areas like Bangladesh and some of the island states in the West Pacific and in the Atlantic, and many islands are making plans to deal with this, because as their land keeps shrinking because of sea level rise, they may completely be underwater in 50 years. So countries like Maldives, Vanuatu, and so on are seriously worried about sea level rise, and many cities like Mumbai, Dhaka, or many coastlines of Bangladesh, New York City, Miami, New Orleans, many European cities, and so on have to worry about sea level rise no matter what the uncertainty is in terms of local projections. Okay.